So think about methane, right? What's the shape of methane? We all know it's a tetrahedral.
Obvious.
And what's the angle associated with methane? Or tetrahedral? 109.5. Okay. It is known that methane is nonpolar.
Yes.
It has all the same angles and all the bonds are the same. However, if you were to draw its orbital diagram, we know C has 2s2 and 2p2, like that. And then for bonding purposes, usually this 2s becomes unpaired and goes to the 2p level to give it 4 bonding spots. Okay? Hydrogen only has one s, one electron. If hydrogen is overlapping with each of these p orbitals, wouldn't one of the bonds not be like the others?
Oh, yeah.
That's true.
Which one would not be like the others? 2s, because s is a spherical orbital. This would be like 2 spheres overlapping, the 2s with the 1s, whereas the 2 p's with the 1s would be those dumbbell shapes overlapping with the s. So one would not be like the others, yet we know that they're all the same.
Yes.
That's where hybridization comes in. That's what hybrid orbitals are. What does it mean for something to be a hybrid? What's a hybrid car?
Yes. Gas and electric.
Gas and electric. What does it mean to be a hybrid?
Mixture of both.
And.
A mixture. A mixture, right? So we mix these orbitals together to form a set of 4 sp3 hybridized orbitals, each with 1 electron, and they're all the same. They have energy between s and p. So S has a little bit lower in energy than P. sp3 is between S and P. Why do you think they're called sp3 hybridized orbitals? Because we took 1 s orbital and 3 p orbitals to make them. So we call them sp3. And those orbitals each overlap with the hydrogen to make 4 equal bonds that are 109.5 and makes a nice symmetrical non-polar molecule. So that's what hybridization is, combining orbitals together to make a mixed orbital state. Now, I have a picture. You don't have to know the pictures, just kind of help you out. But I have here on the left, we have this S and then the 3p orbitals. And you can see one of them would not be like the other. But on the right, we have the 4 sp3. Hybridized orbitals, and they kind of look like deformed P's. And if you were to overlay them all on top of each other, they would all point at the corners of a tetrahedral. Yes?
What is the new electron configuration?
What?
For that? Is there like a new electron?
No, there's no new electron configuration. You don't consider that when you put into electron configuration and all of a sudden have like 1s2, 2sp3, 4. Like, no, there's no special anything for that.
What is this like?
It's a theory used to explain why, instead of having 3 bonds that are alike and one that's different, why the bonds are all the same in something like an octahedral, trigonal bipyramidal, tetrahedral, trigonal planar. So you're going to have hybridization for all those. It's one theory. The other theory is the molecular orbital theory. That's the rest of Chapter 9. You don't need to know that for this course. So when we say we're studying Chapter 7, 8, 9, we're only doing 9.1. You only need to know hybridization. All right, let's look at another example. This has got a little extra special something. Looking at C again, we know that carbon's going to go up, 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 up. Okay? And if we think about, let's just think about one carbon at a time. So let's think about this carbon on the left. What's happening there is that the carbon's bonding with a hydrogen. Get a different color here. Carbon's bonding with a hydrogen, so let's say that's a hydrogen, and that's a hydrogen, and that's the other carbon. Those are the 3 atoms. And the hybridization occurs just with those 3 atoms. So what would the hybridization be?
sp2.
sp2, because we combined 1 s and 2 p's. Now, we're left with this other p. What does that other p do?
stays the same. It doesn't change.
That
P.
other P overlaps with the other carbon's lonely P to make the double bond. Single bonds are called sigma bonds, and this is all on the next page, so just listen for a moment and then I'll let you like write it all down and then we'll kind of go over it again. Single bonds are hybridized and they're sigma bonds. They're called sigma bonds. This hybridization and the shapes are based on the sigma bonds. You know, when you're counting the bonds and unshared pairs for the shape, you count a double or a triple as one, because those electrons stay between those two atoms. But when you take a p orbital and overlap with another p orbital, you form what's called a pi bond, and that's the double bond. Double bonds are always pp overlap. I have this, I know this is a lot, this is the biggest page you have to write today. Let's resume. So, like I was saying, we have in our C2H2, 3 of those electrons are in hybridized orbitals. 3 of those bonds occur in sp2 hybridization. The other p that's alone will overlap with the other carbon's lone p to make that pi bond. Now, I have all that explained on the page, but what it comes down to, you know, I like to give you the background. I like you to know that sigma bonds are SS or sp orbital overlap, and that pi bonds are p overlapping with p. But what it comes down to is you're going to have to look at a molecule and just count and tell me how many sigma and how many pi bonds they have. So to do that, every single bond is a sigma bond. And then if you have a double bond, 1 is sigma, 1's pi. And if you have a triple bond, 1 is sigma and 2 are pi. And I want to show you what a pi bond looks like. This is the molecule I just had drawn. If you look at the carbons, you have overlap with the hydrogens on the outside. And then you have overlap in the middle of the two like sp2 orbitals. So these are all hybridized orbitals, sp2 orbitals. The p that's left, so the ones that kind of overlap in the middle are in line with each other. The p's that are left are in a different plane, because remember you have px, py, and pz. The ones that overlap in the middle make the sigma bond, and those electrons are between the atoms. The pi bond is the overlap of the p orbitals above and below. So in this diagram with the yellow pi bubbles, that's one pi bond. And the pi electrons stay in the lobes above and below. They can be in either space. It's not like one's above and one's below. You could have 2 above, none below. They're always moving, but they stay sort of above and below as opposed to being right in between. That's one pi bond.
Wait, the whole thing? Or
The whole thing. Both yellow bubbles make one pi bond. Because the lobes of the p orbitals go above and below where the carbon is. The one in the middle that makes the sigma bond is overlapping end to end. But the pi bonds are like, the p orbitals are standing up, and it's overlapping above and below.
So when it's a triple bond, it's above and below?
It's madness.
Okay.
Like here. So triple bonding is going to have 1 sigma and 2 pi's, and again, the sigma bond is when they're sort of overlapping end to end in the middle. Those other p orbitals are in different planes, and they're going to overlap, and each pi bond makes 2 lobes. 2 lobes, 1 pi bond, 2 lobes, 1 pi bond, and they're kind of around the other bond. Pulling those atoms together, making the bond shorter.
1 sigma and 2 pi bond?
1 sigma and 2 pi.
And then
And just going back, so you don't get tricked, if I said C2H4, how many sigma and how many pi does it have? Every CH bond is sigma and 1 in the middle. So we would say in this molecule that we have 5 sigma and 1 pi. Because each of these is a sigma. And then in the double bond, we have 1 pi and 1 sigma. It doesn't matter which is which, but that's the way it works. So make sure you count all those outside bonds. All singles are sigmas. A double bond is 1 sigma, 1 pi. A triple bond is 1 sigma and 2 pi. And that's the way it works, because of the way everything overlaps.
Is there ever a quadruple bond?
No. Doesn't work that way. All right. If you remember PCl5, let's go to one more step of hybridization. This gives P a what?
Expanded octet.
Expanded octet. Do you guys remember the shape where it's got 5 bonds and no unshared pairs? It is trigonal bipyramidal. And finally, do you guys remember how it does this?
What do you mean by that?
We have the
What's the D
empty 3D, which is why it doesn't work on level 2. It only works on period 3 and below. And that doubled up electron is kind of promoted to the 3D. It's the same energy level, it doesn't know how far to go. And then we've got 5 bonding spots. Well, these can hybridize also. What would that hybridization be?
Three.
I put together an S,
S3, SP3.
I put together 3 P's,
DSP3.
and I put together a D.
D, okay.
SP3D. Now, I think in your book or in some books they call it DSP3, which is fine also. It doesn't matter where you write the D. Now, are you going to have to draw this out for every molecule to determine its hybridization? No, you are not. There's an easy way to do it. What you do is you look at the center atom and you count the number of pairs, bonded and unshared. And then the powers of the hybridization have to add up to that. Okay? So, for example, if you're doing, let's say, H2O, that is a horrendous drawing. Sorry about that. All right, if you're doing H2O, the O has how many total pairs of electrons? 4 pairs. So that would have to be sp3, because S is 1, P is 3, 1 plus 3 is 4. What if you have like SF6, where it's octahedral?
D2 SP3.
That means it has to add up to 6. So we would use sp3d2, or d2 sp3 would be fine. Okay? So you know on that chart I gave you, the first number is the total number of pairs. Any molecule with the same total number of pairs will have the same hybridization. So like tetrahedral, bent, trigonal pyramidal all have 4 pairs, so they all have sp3.
With 4 pairs of
Electrons. Bonded and unshared.
bonded and unshared.
Doesn't matter, yeah. And make sure when you count for the shapes, you're only counting sigma bonds. Now I can say that instead of being like, oh yeah, triple and a double count is 1. You're really just counting sigma bonds. So when you count the pairs for hybridization, also only count the sigma bonds because the pi bonds are not hybridized. I have a chart. I just kind of whipped this up for you. You're welcome to copy it down, or if you understand that like 3 pairs means the powers have to add up to 3, but I have sort of all the shapes listed here. And I'll leave this up if you want to look at it, but it's got all the info. And I think I also, it's on the like sheet chart for you.